Hi everyone. So today we will be starting Unit 2 and the first topic of Unit 2 is adders and subtractors. So these are the contents of this lecture. In adders we will be covering half adder and full adder, and similarly for subtractors we will be covering half subtractor and full subtractor. So starting with the half adder, it is a combination circuit. This complete Unit 2, every circuit which will be described in Unit 2 will be a combination circuit, and this half adder is also a combination circuit which has two inputs A and B, and there are two outputs sum and carry. That means when these two bits A and B are added, these two are single bit numbers, and when these are added, sum and carry will be produced. So block level representation of this can be shown by this block diagram, and this is the truth table for this half adder, in which we can see that A and B are the two inputs. When these two inputs are added, then 0 plus 0 sum is 0, carry is 0, 0 plus 1 sum is 1, carry is 0, and similarly 1 plus 0 sum is 1, carry is 0, and in the last case 1 plus 1 sum is 0, carry is 1. Okay, so when we find the expression for these two outputs sum and carry, S and C, S, as it can be clearly seen from the truth table, that it exactly resembles the truth table of an XOR gate. So this S is equal to AB bar plus A bar B. This is an expression of XOR gate, and this is also written here. And then carry output, we can easily see that this column of carry resembles with the truth table of an AND gate. So this C is equal to AB. This is the expression for AND gate. Now we can prepare a circuit very easily. When these two inputs A and B enter an XOR gate, we get the sum, and when these two inputs A and B enter an AND gate, we get the carry. Okay, so now coming to the full adder, when we added two single bit numbers, in that case we had not considered the case in which is previous carry, if carry from the previous stage might be there, so we have to consider that as well. That means if we are adding something like this 1 1 plus 1 1, if we are going to execute this, then in that case 1 plus 1 will be 0 and there will be a carry here. So in this row there are three things to be added. So these three things can be considered only when we have three inputs to a set. So here we can see that there are three inputs A, B and C, and when these three things will be added, we will be getting the sum and carry. So this carry is now denoted by C naught, because to avoid confusion, because C is having here, C is now I am having C as an input here. So I have taken the output as C naught. So A, B, C, these are the three inputs, sum and carry, these are the two outputs. So when these things are added together, 000 sum is 0, carry is 0, 001 sum is 1, carry is 0. These are pretty simple cases, and this is also pretty simple. 0 plus 1 plus 0 sum is 1, carry is 0. 0 plus 1 plus 1, that means sum is 0, carry is 1. This can be easily understood like 0 plus 1 plus 1 in decimal. If we see, then it will become 2, and when this 2 will be written in binary, it will be written as 1 0. So from that point of view, it is written sum is 0 and carry is 1. Similarly 1 plus 0 plus 0, we can see that sum is 1, carry is 0, and similarly going to the last case, triple 1, A plus B plus C, sum is 1 and carry is also 1. Because 1 plus 1 plus 1 in decimal, it becomes 3, and when 3 is written in binary, it becomes 1 1. That means this is the sum part and this is the carry part. So now the truth table is complete. We can extract the minterms from this truth table. So for sum, we are having the minterms 1 2 4 and 7. We can see it from this column 1 2 4 and 7, and similarly for carry we are having the minterms 3 5 6 and 7. Okay, so these are written here. This is for sum and this is for carry. Now we will be preparing K-maps for these expressions and then deriving the circuits. So let's go to the next slide. So these are the K-maps. This is K-map for sum. We have fed the minterms. Here it is 1, this is for 2, this is for 4, and this is for 7. So when these entries are made into a K-map, we can see that there is no grouping possible. So we have prepared 4 singles. So when these singles are converted into expressions, we have this expression for sum. I am just giving you an example for this. Let's suppose this one. If you take an example of this thing, so from row element is A is equal to 1. That means we get A. Similarly for this column when we check, we get BC is equal to 1 1. That means A B C. So that's why this term is appearing here, A B C. Similarly we can derive the expressions for all other 3 groups. Now we can proceed for the K-map for C0 carry. So carry is having, as we can see here, that there are 3, 5, 6, 7. There are 4 terms. So this is for 3, this is for 5, this is for 6, and this one for 7. So we can see that there are 3 groups, and the resultant for these 3 groups can be obtained similarly by checking the common elements from the row and the columns. So we get AB plus AC plus BC. So these are the 3 expressions for 3 groups, and when we club these 3 expressions, we get the expression for C0 carry out. Okay, so now we can prepare circuit for this. As we can see from these expressions that there is a variable A, there is a variable B, there is a variable C, and here we can see that A bar is being used, here we can see B bar is being used, and C bar is also used here as well. So we have taken 3 NOT gates to prepare A bar here, B bar here, and then C bar here. Now as and when required, the variable which is required to generate the product will be taken from these positions, and product will be generated with the help of an AND gate. So for the first product A, B and C, we can see that we have taken these 3 variables to prepare A, B, C product. Similarly for this second product A, B bar, C bar, we have picked A from here, and then B bar from here, and then C bar from here. So to generate this generates my second product. Similarly other 2 products are prepared, and when all these 4 products are ready, I can see that these are to be summed, like we can see here, and this logical addition will be performed by OR gate. Now as there are 4 things to be added, so I have taken a 4 input OR gate which will provide me my sum. Okay, similarly for carry, we can see that there are 3 products, and each of the product require 2 variables. So we have taken 3 2 input AND gates. This generates AB, this generates AC, and this generates BC. And when these 3 things are added, AB plus AC plus BC, this gives me my final carry C0. Okay, so this is full adder circuit in terms of basic gates. Now we will proceeding to the another version. Similarly we can prepare this full adder using NAND gates only, using NOR gates only. So if we are interested in preparing this full adder using NAND gates only, these AND gates and this OR gate will be replaced by NAND. Similarly for the carry as well. And these NOT gates will be replaced by the NAND equivalents, something like this. This is the NAND equivalent of a NOT gate. So these 3 NOT gates will be replaced by the NAND equivalents, and the AND and OR gates will be replaced by the simple NAND gates. As it is well known that AND OR realization is comparable, is exactly similar to the NAND AND realization. So now coming to the next part of it, full adder using 2 half adders. So it can be easily understood by taking an example. So if we are having 3 things to be added, let's suppose these 3 things are 1 plus 1 plus 1. So these are the 3 things to be added. So let's suppose this is A and this is B. So when these 2 things are added, 1 plus 1, then I will be having a sum, I will be having a carry. Then sum will be 0, carry will be 1. So if I take these A and B and use a half adder to generate this sum and carry, so this will be 0 and this will be 1. Now the half of the addition is done. Now I have to add this 1. This 1 will be added to the previous sum. So 0 plus 1 will be 1, and finally there will be no carry. So I am getting the final sum as 1, and there are two carries. For in the first stage addition I am getting carry as 1, and in the second stage addition I am getting carry as 0. So this is half adder 1. Half adder 1 generated 0 plus 0 and 1, and when this 1 as C was added using another half adder, so 0 plus 1 from here, this is C. So when these two things, previous sum and this carry, are being added by another half adder, it produces the sum for the second time, which is the final sum, as there is nothing left to be added. So this becomes the final sum, and carry are 2. This is the first stage carry and this is the second stage carry. We can see that this second stage carry is 0, so I am placing a 0 here. So in the first stage carry was 1 and in the second stage carry is 0, but in any of the situations, if carry is generated, either is it in the first case or it is in the second case, it will be considered. So that means this is logical addition of these two carries, C1 plus C2. This becomes my final C out. So this is the concept of half adder. Sorry, this is the concept of full adder using two half adders. Similarly, we can replace these half adders. The block of these half adders can be replaced by their actual circuit level equivalents. So we can see that sum was obtained by an XOR gate. As we can see here, this becomes my S1, and similarly this AND gates generate the carry part. This becomes my C1. Okay, so this is sum and this is carry. Similarly, I can see here that this S1, we can see here this S1 was added with this C using another half adder. So this S1 and this C from here, S1 and C are added again using another half adder. Okay, so this is the second half adder and this generates the final sum. So this is final sum, and this AND gates produces another carry C2, like here C2. So now there are two carries to be considered, C1 and C2, and these carry C1 and C2 are added together by the help of an OR gate to produce the final carry. So this becomes my full adder using two half adders. Expression for these can also be obtained by arranging the K-map expression into XOR related things. So this can be done also. Now we will be proceeding to half subtractor. So similar to the half adder, this half subtractor is capable of subtracting two single bit numbers. These two single bit numbers are again A and B, and there are two outputs, difference and borrow. Like in the adder case, we are having sum related outputs, sum and carry, but in subtractor we are having difference and borrow. So when we look at the block level representation of this half subtractor, we can see that there are two inputs, A and B are the two inputs, and there are two outputs. These are the two outputs, difference and borrow, and these are the two inputs, A and B. Okay, so inputs A and B and outputs D and B naught. B naught represents the borrow. So to avoid confusion, there is this naught is appended here to avoid confusion with this input side B. Okay, so performing subtraction of these numbers, 0 minus 0, first we will be considering the simple cases. 0 minus 0, the difference is 0, borrow is 0, and then skipping this second case and then going to the third case. 1 minus 0, it is very simple also, difference is 1 and borrow is 0, and then 1 minus 1, it is also simple, difference is 0, borrow is also 0. Now this case which we had left, 0 minus 1, is a bit tricky, because it is very clear that 0 minus 1, that we are subtracting a larger number from a smaller number, then definitely borrow must be there. So it is confirmed that borrow will be there. So 0 minus 1, borrow is there, but how this difference is 1? So For this we have to take this example. When we are subtracting something like this, let's suppose we are subtracting 1 0 minus 1. So 1 0 minus 1, 0 minus 1 is not possible, so we take a borrow from there. So when we take a borrow, this 0 becomes now 1 0. Now 1 0 is equivalent to your 2, and when we subtract 2 minus 1 we get 1. So that's why we are writing a difference is also 1 and borrow is also 1. So this is the justification of the truth table. And again, this truth table can be converted into expressions very simply, as we can see that this difference expression is again very similar to the sum expression which was obtained from for half adder, and it is similar to an XOR gate, AB bar plus A bar B. And similarly we can see that B naught is having a single term like for the carry case in half adder, but the expression is different this time, as we are having this one here, this one. Now this one in borrow corresponds to this A is equal to 0 and B is equal to 1. So we can consider that A is, we can have a bar only, and B will be non-bar. So A bar B. So that's why we have written here B naught is equal to A bar B. So these are the two expressions for difference and borrow, and when these expressions are converted into circuits, we can get this one. So A and B are the two inputs. When these two inputs are being added, when these two inputs are being subtracted, then this XOR gate is providing me the difference of these two inputs, and this A bar B part, A bar B thing is generated by this, A bar is generated by this NOT gate, and this A bar when multiplied by B gives me the borrow for half adder. So this is the half subtractor circuit. So this is a normal realization of half subtractor. Similarly, examiner can ask you to prepare the NAND version of this half subtractor or NAND version of the previous half adder or full adder. So now we will be extending this concept of half adder to half subtractor concept to the full subtractor. So this is the full subtractor now. Again, like the case of full adder, it is having three inputs A, B and C. And this previous here C is the previous stage borrow. Like in case of carry, there was a previous stage carry. Here C will be treated as previous stage borrow, and whenever we are subtracting, outputs will be two, difference and borrow, produced by the subtraction of these three bits. So actually what we will be doing here, we will be doing this A minus B minus C. Okay, or we can say that we will be subtracting, or we can write it as A minus B plus C. Actually we will be doing this. So this expression I will be using to prepare the truth table for this full subtractor. So these are the three inputs A, B and C. So 0 minus 0 plus 0, though this thing is actually 0, 0 minus 0, difference is 0 and borrow is also 0. Similarly 0 minus 0 plus 1. So I am actually doing this 0 minus this. So 0 minus 1. Now from the half subtracted table, it was very clear that 0 minus 1, difference is 1 and borrow is 1. Similarly, this is also the same case. 0 minus 1 plus 0. This is also difference 1 and borrow 1. Then 0 minus, actually this becomes 2 now. So 0 minus 2. Now 0 minus 2, to do this, it is very clear that we are subtracting a greater number from a smaller number. So it is very clear that there will be a borrow. Okay. So when now 0 minus 2 is not possible. So I will take a carry. Now when I will take a carry, it will become 1 0. This 1 0 is equivalent to 2. And when this 2 will be subtracted from 2, I will be getting a 0. So that's why I have placed difference as 0. Okay. So now proceeding further, 1 minus 0 plus 0, it is very simple. It will remain 1, borrow will be 0. And similarly 1 minus 0 plus 1, that means 1 minus 1 effectively. So difference is 0 and borrow is also 0. And then 1 minus 1 plus 0. So 1 minus 1, effectively it becomes then 0, 0 again. And now 1 minus 2, this This is equivalent to 1 minus 2. So 1 minus 2, we are subtracting again a larger number from smaller number. So that's why borrow must be there. And then if we look at this position, so difference is 1. How this difference is 1? Because 1 minus 2 is not possible. So again, we can calculate it. 1 minus 2 is not possible. So 1 minus 2 is not possible. So in binary terms, if I write, it will be 1 minus 1 0 actually. 1 minus 1 0 is not possible. So I'll take a borrow. So when I take a borrow, this will become 1 0. Now if I perform 1 0 minus 1 0, so this will become, sorry, this was 1, and if I take a borrow, this becomes 1 1. So this 1 1 actually becomes 3, and now 3 minus 2 becomes 1. So that's why I have written a 1 in the difference column. And similarly, by checking these columns for D and B naught, we can write the minterm expressions. Difference is 1, 2, 4 and 7. As we can check from there, this is 1, this is 2, this is 4 and this is 7. And similarly for this B naught, the terms are 1, 2, 3 and 7. Okay, so let's now move to the K-map part and the circuit part of it. So this is a full subtractor. This is 1, 2, 4, 7 is the difference part. B naught 1, 2, 3, 7 is the borrow related minterms. And when we solve this, then we can see that this difference expression is exactly similar to the sum expression of the full adder. There is no change absolutely. And when we compute K-map for this borrow, then we get 3 groups. And these 3 groups, answer can be written. I am just mentioning an answer for this one group, this group, if we want to check. So this group involves these 2 columns. These 2 columns are having this 1 in common, and this one corresponds to C. And these 2 ones involved in this group have A is equal to 0 in common. That means A bar. That's why it is written A bar C. So this A bar C is appearing like this. So similarly, we can compute this A bar B and BC as well. So just like the case we had prepared the full adder using 2 half adders, we can prepare full subtractor using 2 half subtractors, and that basic gate realization is left as an exercise for you, because it can be prepared simply. Like we had prepared the full adder using basic gates, we can have A, B, C, and we can have bar for those A, B, C, and then we can generate products using OR or AND gates, and then whichever product we want to add, they can be added using an OR gate. So now coming to the full subtractor using 2 half subtractors. So we can see that these A and B are entering a half subtractor. This is half subtractor 1. If you want to prepare the block diagram level representation of this can also be prepared. I will prepare it just below this circuit. So if we are interested in preparing the block level representation, so this half subtractor 1 will be having 2 inputs, HS1, half subtractor 1. A and B will enter from this half subtractor 1, A and B, and it will generate difference 1 and B naught 1, borrow 1. Okay, but there is third thing also to be subtracted. So this third thing will be taken into consideration by another half subtractor. So we have taken another half subtractor HS2, and this will again produce a difference D2 and B naught 2. Okay, so there is nothing more to be subtracted. So this D2 becomes the final difference, but there are 2 borrows, this B naught 1 and this B naught 2. So just like the case in full adder, these 2 borrows now will be added logically using an OR gate. So in whichever stage borrow is generated, it will be considered for the final borrow. So this becomes my final borrow B naught, and this is the internal structure of half subtractor 1, and this is the internal structure of half subtractor 2, So we have replaced these internal blocks of HS1 and HS2 by their internal structures, and this OR gate is appearing as it is here. We can see that. So we can see that this OR gate is appearing as it is. So there is nothing more left now. So this prepares my full subtractor using two half subtractors. So with this we come to the end of this lecture of half address and half adder, full adder, half subtractor and full subtractor. And in the next lecture we will be taking into consideration the 4-bit parallel address. If you want to add multiple bits, then how to proceed about that. Thank you very much.